Okay, let me comment a little bit on the Monte Carlo thing, what I was looking for or getting at. So like, here's the coral reef here. So say the sun's back here, that's gonna make a shadow here. So as you move your sensor along here, so here's the X direction. Out here, you're in the sun, you come in here, and now you're in the shade. Or if you're doing a profile this way, here you're in the sun, and then somewhere you go into the shade. But on the plots where it just showed like the sun versus the shade and things started changing at 8 meters, you need to know like what was the depth of the instrument and something like this, so I could say, oh, this was 8 meters out, that's where I went into the shade. Because if the instrument was up here, I wouldn't go into the shade until I was 1 meter from the reef. And if it was down here, maybe I'd go into shade when it was 15 meters from the reef. So you just need to add that kind of information. So when somebody looks at the plot, they can say, oh yeah, I see, that's where the instrument went into the shade or whatever the case might be. So it's just a minor addition, but it just helps you, whoever's looking at your paper, that they have a visual impression of seeing, oh, here's where the instrument was doing whatever. And or if you were measuring ED with an instrument pointing upward and you move into here, or you measure ED with the instrument looking that way and you move into the shadow, or the instrument's looking towards the reef and you move into the shadow, all of those will give you different irradiances, because in this case, you're looking kind of out at the sunlit ocean. If you're looking this way, you're looking at the dark reef, and you're going to see those effects will start, you know, at different distances from the reef and so on. So that's all that needs to get said there. Okay, so let's fire this thing up. And wherever the pointer went. Okay, so today we're going to talk about surfaces. And we'll finish off our big organizational chart. You're now all masters of everything except what's in this box here. And so we're going to talk about modeling the sea surface and the bottom. And that gives you boundary conditions that you need to plug into the radiative transfer equation to solve it and compute all this other stuff. And there's other possibilities, internal sources like bioluminescence that aren't going to get discussed in here. So anyway, there's where we're going today. And there's this thing we've mentioned called the bidirectional reflectance distribution function, the BRDF. It's how you describe reflectances by any surface. We'll define that, talk about it. We'll talk about what a Lambertian surface is. And you've been hearing that word from the first day of class. We'll talk a little bit about you know, the air-water surface, this thing called the n-squared law for radiance. We'll talk about how to model random windblown surfaces. There's this thing called the Cox-Monk model. There are fancier ways to do it. So just kind of walk through that. So at least you've seen the words and you can forget it all, but then 5 years from now, you can come back and look again. So the business of the BRDF, the volume scattering function tells you how light's going along, it interacts with the particle, and it scatters off into some direction. The BRDF does the same thing for surfaces. Light's going along, it hits the surface, and it reflects off in some direction. So it's just sort of a volume scattering function for surfaces. And so it's an IOP if you wish. And you can define a BRDF for any kind of surface. So the way you can think of it is, here's a surface that could be the surface of the wall, it could be the surface of the ocean. You've got radiance coming in at some incident angle theta I and some azimuthal direction phi I, and the surface reflects the light off, and you have radiance going out in some reflected direction. So I'll call that theta R and phi R, and there's some angle phi in between the incident and the final direction. So, and in general, a surface will reflect light into all directions. Okay, The way this thing is defined is it says, look, I've got some radiance coming in my incident direction. And then I'm going to put this cosine factor in here, because what I'm going to do is when you have radiance coming from this direction, and it's so many watts per square meter per nanometer, that per square meter is on a surface perpendicular to the direction the light's going. When I'm working with surfaces, I always like to think of the surface, let's say a horizontal surface. And so there's a cosine factor between the surface that's defining the radiance inside the detector and the horizontal surface I'm talking about. So that's where this cosine factor comes into. And then this radiance is being collected in some little element of solid angle if I'm pointing my instrument this direction. And so I have a little bit of element of solid angle, and that reflects a little bit of element of radiance dr reflected going off into that direction. So it's simply the definition says, take this little bit of reflected radiance that's coming from the incident radiance, it's a little element of solid angle, and divide that, and that's the definition of the BRDF. Now, that's what the mathematicians like me, like Ken Voss, will tell you, well, when he measures it, you simply take a measurement of the reflected radiance, point your instrument looking at the surface, and well, what does this thing look like? That's just ED onto the surface. So he'll set up an instrument, he'll measure ED, if what's all the light going onto the surface. Oh, I'm sorry, this ED is from a particular direction. So the ED your instrument measures is getting sunlight from all directions. What you want to do when you make this measurement is just have a light source in one direction. And what does that contribute to ED? So it's ED from the radiance in the incident direction. And then if you took all the incident directions, you would get the kind of ED you measure when you go outside. So anyway, it's just take the incident irradiance ED onto the surface from light in a particular direction and look at the radiance that's reflected into some other direction, and that ratio is then the BRDF. And then, of course, this thing is a function of all incident directions and all reflected directions. So to really measure the BRDF, you have to set up an experiment where you have your surface here and you've got a light source, and you move the light source for all different directions, and each one of those you measure ED, and then for each incident direction, you have to measure how much radiance is reflected into all other directions. So it gets to be a major undertaking, and that's why it's almost never measured in the field. Ken Voss cooked up a little gizmo one time that he could set on an ocean bottom, like on a sandy or muddy bottom, and it had little light sources around it and little measuring, little radiometers looking in different directions. And he would actually measure the BRDF of a sandy bottom surface, but that's kind of a once in a lifetime thing that gets done. Now, the way this gets used in radiation transfer theory, here's our definition. So if you ask me, I give you the BRDF of the surface, how much radiance is this surface going to reflect? Well, I go back to the definition. If I just multiply through by this, and I integrate over all of the incident directions here, I'm looking at one reflected direction, and I've got light going onto the surface from all incident directions. Then I would just take this guy, integrate over all of the incident directions, and then say, for this incident direction, the BRDF says this is how much is reflected into the direction I'm interested in. From another incident direction with that radiance, then the BRDF tells me how much is reflected, and so on. So the reflected radiance from the surface says take the incident radiance from all directions times the BRDF, integrated over all the incident directions, and that'll tell me what's the measurement of the reflectance from that surface due to light coming from all directions. Okay, so that's the way it actually gets used in the theory stuff. Okay, So the BRDF, it's got units of radiance over irradiance. So that's units of per steradian. That's the same as the remote sensing reflectance, LW over ED, which has units of per steradian. They're not the same thing, because when you go outside and make an RRS measurement, you're getting ED from all sky directions, and you're looking at the water leaving radiance in one direction. Here, you're getting ED, the contribution to the total from one particular direction, and you're looking in one particular direction. So they have the same units. They're kind of conceptually look the same, but numerically, those will be different quantities. Okay, what's up next here? Yeah, when you can actually use hydrolite, and like if you wanted to compute the BRDF of the ocean, what you would do is a bunch of hydrolite runs where you put the sun in the black sky, you put the sun straight overhead, do a hydrolite run, it gives you water leaving radiance in all directions. Then you move the sun over here, do another hydrolite run, get the radiance in all directions, move the sun here, another run, and then screw all of those pieces together, and you would eventually come up with a BRDF of the sea surface for that would work for any angle. That's how that sort of thing gets computed. Here's just a couple of examples. Put in a wind speed, case one water, et cetera, et cetera. And here's one, it's a little hard to read, but this is the BRDF for the total upwelling radiance, or computed using the total upwelling radiance. And the sun was over here. So this is theta and this is phi. I put the sun in here, and you see there's this big bump here in the BRDF. That big bump is simply when the sun's over there, 180 degrees away, I see that bright specular reflection coming off the surface. That's all that is. If you wanted to just use the water leaving radiance, then you don't see this big bump because there's no specular reflection. And you see, here's what, with the sun here and the specular point over here, here's this BRDF for the water leaving radiance. And people use these kind of things in all sorts of applications and modeling and so forth. You'll notice, we'll learn in a minute that a Lambertian BRDF means that the reflected radiance is the same in all directions. Well, you'll see here, it's actually not, but it's not too far away. We'll see some more of that in a minute. Anyway, you will see these sort of things used. Okay, so this business of Lambertian BRDFs is kind of confusing. So you'll see some people, or you'll read a paper and they'll say a Lambertian surface reflects light equally into all directions. Lambertian surfaces are therefore called isotropic or uniform or perfectly diffuse reflectors. And then you'll read another paper and it'll say a Lambertian surface reflects light with a cosine angular distribution, and therefore the Lambertian surfaces are also called cosine reflectors. Well, your mental image, at least for me, is if I read a paper and it says it reflects light equally in all directions, I think of light coming in and it's going off the same in all directions. Well, if I read this and it says it's a cosine reflector, I think of the light coming in and then it's reflecting off in a cosine pattern. So which is right? This is another place where for light, you got to be exactly precise on what measure of light you're talking about. That's why I put it in parentheses. So actually, both of these statements are correct. The correct statement is that each point of a Lambertian surface reflects intensity. Remember, intensity is power per unit steradian. Reflects intensity in a cosine pattern, and it reflects radiance equally in all directions. So what's going on is I've got a radiometer, I'm looking at the surface and at some viewing angle theta. Well, at a particular point on the surface is reflecting light in this cosine pattern, but the light is being described by the intensity not by irradiance or radiance. It's reflecting it power per unit solid angle. And then every point on the surface is doing that. So then, as I move my radiometer from this angle, I'm seeing this area of surface. But if I move the radiometer further out, I'm seeing a bigger patch of surface that's proportional to the cosine of the angle. So I look straight down, I see a little bit of surface. I look over here, I see a bigger patch of surface by a factor of 1 over the cosine. So the cosine dependence of the reflectance intensity times the 1 over cosine reflectance of the area seen by the radiometer, those cosine factors cancel out. And then the radiometer, which is measuring radiance, says, oh, I see the same radiance independent of the direction. So you have to be careful on exactly how you're measuring this word light. But both of those statements is correct. The surface reflects radiance equally in all directions, and each point of the surface reflects intensity in a cosine pattern. Okay, so then what's a Lambertian surface? Well, the BRDF for a Lambertian surface says that the radiance is reflected equally in all directions, and it's described by a reflectivity rho, and then there's a factor of pi that came in here. We'll see in a moment. But anyway, this is the BRDF for a Lambertian surface. It's very simple. And if rho was 0, it's a black surface. If rho is 1, it's a perfectly reflecting or white surface. So to see how this works, if you go back and say, well, what's the irradiance reflectance? EU over ED. Well, that's just integral of reflected radiance times the cosine and integral of incident radiance times the cosine. But what's the reflected radiance here? Well, you go back, that's just, you know, wherever it was, this equation right here. So for the reflected radiance, I will plug in that equation right here. Here's reflected, and here's that integrated over all incident directions for the given reflected direction, and then integrated over all the reflected direction to get EU and ED. Well, if the BRDF has this simple little form, that just comes out and you have this thing here and this thing here. And if you go through and do the calculus, those things just are the same. They cancel out, and actually it's equal to pi, so that the irradiance reflectance of a Lambertian surface is just this reflectivity rho. So when you want to model a Lambertian surface like an hydrolite, and let's say you want to figure out the reflectance of a sandy bottom, just go out and measure the irradiance reflectance EU over ED. So you put your instrument there, you get EU or ED, you turn it upside down, you get EU, take the ratio, there's your reflectance, stick that in there, and there you have the BRDF of the Lambertian surface, and that's what's the default in hydrolite. So that's why when in the hydrolite database, there's a bunch of spectra for, you know, typical corals, sand, leaves, seagrass leaves, etc. They're just the irradiance reflectance of those substances. And then hydrolite takes them and says, stick it in here and assume that the RDF of that bottom is Lambertian. Okay, enough said. So there's some of those spectra there, and away you go. Hydrolite doesn't have to have a Lambertian bottom, but 99 out of 100 times, that's what people assume. Okay, enough said there. So the question then is, who are the world experts on BRDFs? Like people in the paint industry, because they need to know BRDFs of different paints. Is it military people? You know,
That's what is it people who are designing like stealth fighters and ships?
yeah, so the stealth fighter people need to know about the BRDF of their invisible airplane. All of those people, they are total amateurs, poverty stricken. The people that really know about BRDFs are the movie people. Okay, so you make a movie with some, you know, computer generated image here, you start out and you make what's called a wire grid of the thing. And in each little patch of this face or the hair or the clothes, you stick in the appropriate BRDF that describes reflectance by skin, clothes, hair, buildings, whatever, and stick all of that together. Guess what? Monte Carlo ray tracing that says, I've got the sun up here and I'm looking at this person and her face is in the shade or in the sun. The BRDF tells me how the light's reflected and tells me what I see. And guess what? They do backwards Monte Carlo ray tracing. So they say, I'm looking over here, I'm going to send out all of these rays, bounce them off of all the BRDFs of all these little pieces of face here. Some of those will go up and hit the sun, etc. And I'll generate an image of what that looks like. And it's phenomenal how realistic it can be. So it's basically what you get here is 20 years of research by Pixar and, Lucas and Spielberg and all these guys. And, what the heck, 20 million bucks, you need some new computers? Sure, no problem, go ahead. So, and in my world, oh my gosh, I just got $100,000 from NASA, I'm in Fat City. 100,000 bucks wouldn't support Lucas and Spielberg for half a day. So anyway, that's all it amounts to. All of that stuff is Monte Carlo ray tracing and BRDFs. And they have these huge libraries of those things. Here's a BRDF of the sun setting over the ocean, and they put in, a wind dependent, the wind speed is increasing. So you see a little bit difference here in how the ocean is reflecting light. And so there's a level surface and you see there's waves coming up on the water here. And they're just using a BRDF, just like I showed you a minute ago, of the ocean surface reflectance, basically, to generate an image like that for a movie. So to put it in perspective, so there was a movie a few years ago, and since I don't have any kids, I never saw it, but it was called Monsters University, 2013. Generating that movie with all of these little monster thingies took 100 million hours of CPU time. This was at Pixar. They had 24,000 computer processors running for 2 years to generate that one movie. That's what I'm talking about. That's serious ray tracing. And then you get a movie and, they've got a BRDF for the green guy or the blue guy or the purple guy, and for the brick walls back here, and for the tree bark, and for the marble steps or whatever. And it's just the way it works. It's incredible. Okay. Here's more stuff that is getting to the point now that you cannot tell a computer generated image from a real person. And so this is a New York Times article 2 years ago, where there was an article about these people, which are invariably beautiful women. Nobody seems to care about ugly men. So anyway, and there's a distinct market for this that is not including women and whatever. But anyway, the article was about these computer generated people have all their Twitter feeds and all of this kind of stuff, and people follow these and they post their political thoughts or whatever it is, or their dating advice or whatever. And people are following this and not even realizing these are not real people. These are a neural network computer or a neural network that's answering your questions, and they're generating these figures. And in this article, there was a comment from a guy, or they had interviewed a guy, and he said, oh yeah, I have whatever her name is there, she's my girlfriend. And, she answers all my questions, and we have, chat sessions and all of this. And he said, I'm just in love with her. And the interviewer said, well, dude, that's not a real person. That's a computer program. And the guy said, quote, I don't care as long as she loves me, unquote. And I just thought, man, I thought I was like a loser in high school, but at least my girlfriends were real people, So anyway, So here's an article from the New York Times about a couple of days ago, or no, actually, I guess it was longer, on the generation of faces here. And let's click on this website here and bring that up. Okay, so it's an article. Okay, nice looking person there. As you scroll down through the article, the faces, every one of these is computer generated. There's not a single photo of a real person used here. And they all look, they're indistinguishable from real people. And so it gets down here, and then the rest of the article somewhere talks about you can buy one of these faces for $2.99 or 1,000 people for $1,000. And you can stick those on your, let's say, your political ad the next time you see a Trump rally or a Biden rally or whatever, and they've got all these people and they say, oh, I love Donald Trump, or I hate Donald Trump, or whatever. You have no idea if that's a real person or computer generated thing put together by some marketing agency that was hired by whatever company it is. So it's a really scary thing, I think, because it means you absolutely cannot trust anything you see now that says, oh, here's a person that says whatever. You literally can't tell if it's a real person or it was just made up in the back office by some, hacker doing whatever. So enough said there. It's a new world that's just the way it works. Okay, so in reflectance terminology, talking about all these things, you look through the literature, there must be 20 different kinds of reflectance. And of course, every field, like the paint industry and the oceanographers and all of those guys, they've all developed different terms for the same thing. But in theory, the word reflectance is always supposed to have two adjectives before it. The one that describes the angular distribution of the source of the incident light, and the second that describes the reflected light. So the BRDF is a bidirectional reflectance. It has one particular incident direction and one particular outgoing direction. And then you vary those over all the incident and all the outgoing directions. But it's measuring a radiance. It's telling you how radiance in one incident direction is turned into radiance in one reflected direction. Now, the remote sensing reflectance, RRS, that's LW over ED. That's a hemispherical directional reflectance. The incoming light ED is coming from the whole hemisphere of directions, and then you're looking at LW in one direction. So the irradiance reflectance, RRS, is a hemispherical reflectance, because the ED incident is coming from the whole hemisphere, and you're looking at the reflected light that gives you EU in a whole hemisphere. So when you read these books on, like there's one by a guy named Hopka called Theory of Reflectance and Emittance Spectroscopy. Yeah. He defines 10 different reflectances and albedos, not one of which correspond to what we oceanographers use. But he'll always be talking about, oh, we measured the hemispherical directional reflectance of the lunar surface or whatever. Well, you have to really pick through it and figure out what it is he actually measured. He's telling me, you just have to understand the terminology. Okay, on to water surfaces. So here's the air, here's the water, different indices of refraction. You have incident light coming in, incident light reflecting, incident light going into the water. That could be radiance or it could be irradiance. Or if the incident light is coming from below the surface, some of it can be transmitted through and then some reflected, or you may have total internal reflectance where there's no transmitted light, it all gets reflected. And you've all seen this stuff in freshman physics where there's this law of reflection that says the angle of reflection equals the angle of incidence. And then there's Snell's law that says N1 sine theta 1 equals N2 sine theta 2. And the poor guy's name really is Snell. His name was Willebrord Snell van Ruyden, Willebrord Snell of Ruyden in the Netherlands. Well, he's Dutch, and in those days, back in the 1600s, you're always published in Latin. So Snell became Snellius when he published his papers in Latin. And then when they started in the 1800s publishing in German, then Snellius got turned into Snell, S-N-E-L-L, instead of back to what it really is. And some people like George Cadwar are on a campaign to quit calling it SNELL's law and call it SNEL's law. And I sympathize with that, but I'm afraid it's a lost battle because I'm not going to worry too much about it. But anyway, so, and then if you have air incident light, you can compute the transmitted directions here. If it's water incident, you can compute the transmitted directions or figure out that it's too far out and it'll be totally internal reflected. You know, that's the basis for all light calculations of how light is reflected by sea surfaces, because I've drawn this for a level surface, but if this is the little tilted facet of a wave surface, it's the same physics. It's just not this angle, it's like this angle. So you've all seen that. You should have that in the back, you know, tucked away in your brain because it gets used every day. And of course, when you go back and look at these angles here and you realize, well, you only get transmission up to a certain point and then it's 100% reflected. And then you've seen these curves in your freshman physics book where it talks about this Fresnel's law that tells you what fraction of the light is reflected as a function of incident and transmitted angles. And so if it's air incident, it's maybe 2% or so. And of course, that depends a little bit on wavelength because the index of refraction depends a little bit on wavelength. So for air incident light, it sort of starts out at 2% and then eventually goes up to 100% if the light hits the water surface exactly horizontally. If it's water incident, it starts out the same, but then by the time you get out to this angle of about 48 degrees, it's 100% reflected. There's no transmitted light. So that's where all of that stuff comes from. I think you probably are all familiar with that. Now there's this thing that comes out of that called the n-squared law for radiance. And if you think of, here's the water surface, this is air, this is air, this is water. And you sit here and you map out a little bit of solid angle, some little delta theta, delta phi solid angle. And remember, there's our little element there, the sine of theta, delta phi. And then you apply Snell's law to the boundaries of this little rectangle. So this angle is going to come through and be that angle. This angle will come through and it'll be some angle here. And then down here, there's a little solid angle here, delta theta 2. That's going to be the sine of theta 2, delta theta 2, delta phi. And so the catch, though, is because of refraction, this solid angle here will map into a smaller solid angle in the water, just because of how refraction works. Well, you go through and you do a little bit of math here, and you say, okay, I'm putting in a radiance up here, and it's, you know, power per square meter per unit solid angle. And then that same power, a little bit will be reflected by the surface, maybe 2%, but most of the same power will go into the water. And so it's the same amount of power, but now it's a smaller solid angle. So the radiance will increase when you go through the surface because you have the same power, same energy, but you've compressed that into a smaller solid angle. So you go through the math here, which we won't bother with, but you end up with this thing called the n-squared law for radiance. And what it says is what's conserved when you go across a surface. Well, energy is conserved. Radiance is not conserved. It's radiance divided by the index of refraction squared. That's actually the conserved quantity. And then you may lose a little bit to reflection at the surface. So in this case, if I have some radiance L1 here, and that's actually, yeah, L1, and it's within medium within 1. And then I transmit some fraction of that into the surface, and I have L2, and that's a value of index refraction of L2. That's what's conserved. So you remember, it's not the law of conservation of radiance, it's the law of conservation of energy. So what this thing tells us is, if you go back here, remember on the day 1, I said, this looks kind of weird. Here's radiance as a function of wavelength at selected depths in the water. And in the air, I have some value here. Sorry, that's the black line is in the air. But then if I go just below the surface, it's a bigger radiance. And then here at 10 meters, well, it's dropped down here, but off at the visible wavelengths, it's a bigger radiance there. And then it eventually starts dropping off with depth. So what you're seeing here is that n-squared law effect. This sky radiance, the black line, goes through the surface and it becomes a bigger radiance value because of this n-squared law. And then as you go down with depth, absorption begins decreasing the values. And I don't know how many times I've had people send me something like this and say hydrolite's wrong because the radiance in the water is bigger than it was in the air. And no, that's actually the proof that hydrolite is correctly modeling the sea surfaces. And then they say, oh, well, I didn't know about that. So, okay. Anyway, so there's these fellow Cox and Monk, Chip Cox and Walter Monk. And Walter's my hero because he was still publishing papers at 101. And I'm only 74. So I have like 25 more years of science. So anyway, what they did was they flew an airplane, they went out and they took photographs of glitter patterns. So here's one of their photographs. The wind speed is in this direction and the sun's off kind of behind them. And they're looking at the glitter pattern. And they did this with a lot of different wind speeds. They had some ships in the water that were measuring the surface wind speed and that sort of thing. And then they cook up this mess of a coordinate system where they say, from my geometry, I know where the sun was, I know where I'm looking. And for me to see a little bit of glint right there, there had to be a wave facet that was tilted in just the right way to reflect the sun up towards me. And so you read their papers, they've got these coordinate systems and they work backwards and figure out what are the slope statistics of the sea surface that would generate this particular glitter pattern. And then you do that as a function of wind speed. And then it eventually boils down to some very simple equations, which says, I'm going to talk about the slope variance in the crosswind direction, sigma sub c, and the slope variance in the along wind direction of sigma u. And then there's a total variance, which is the sum of those. Well, it turns out that the along wind variance is basically 3.16 times 10 to the minus 3 times the wind speed. The slope of the crosswind waves is 1.92 times 10 to the minus 3 times the wind speed. And the wind speed is always what they call mast height, which is 10 meters or something like that. Sometimes they use 12.5 meters, but anyway, you read that in a paper. But they came up with these really simple little equations that relate the statistics of the slope of the surface to wind speed. And these actually do a really good job of generating sea surfaces that you can use to then do Monte Carlo ray tracing to compute reflectances and transmissions of the surfaces. Now, what happens here is they're only giving you the slope statistics. They don't tell you anything about the vertical elevation statistics of the water, but it's the slope that matters because the sun's over there, I'm looking down there, it's whatever the slope of that wave is, it reflects the light. And whether it's in the trough of a wave or up here really doesn't matter. On the other hand, visually, when you go out and look at the ocean and you say, wow, those are big waves, you're really looking at elevation statistics, not at the slope statistics. So for optics, it's the slope that matters. And so there's ways where you take their statistics, draw random numbers, and what you do is you draw like 3 random numbers and you determine the elevations of this little triangle and according to the slope statistics. And then you draw another random number and you make another little triangle. And then you draw another random number and you make another little triangle. And you do that over a patch of sea surface and you generate all these little triangular wave facets that have the same slope statistics as the real ocean. Then you do Monte Carlo ray tracing. Well, the catch is here's a Cox-Monk surface, and that just really doesn't look like a real sea surface because it's all these little crinkly, sort of think of them as capillary waves if you wanted, but they're not really, they're just slope statistics, but there's no elevation. A real sea surface, you have the little bitty waves are on top of bigger and bigger and bigger waves. And so you get something that looks like this. Now, the catch is if you want to generate a proper sea surface, including both elevation and slope variability, then you have to go take a class in Fourier transform theory. Then you have to go be a physical oceanographer and learn about what are called wave elevation variance spectra. And then you spend like 3 months, like I did, trying to program all this stuff up and get it to work, but you can eventually do it. And so in the process of doing that, I found out that there's not a single textbook or paper that actually tells you what you need to know to write a computer program. They never show you the factors of 2 and the square roots of pi and all of that kind of stuff. And then they always say, oh, well, we're going to normalize things at the end anyway, so we don't care about the units. And oh, it was a nightmare. But I finally got it to work. I put together this big tutorial that says, here's how to do it. You can go there and, you can download the computer programs and all of that. Or you can read these 3 appendices in the Ocean Optics web book, which are like 50 pages a piece to get you through all the math. And I know you'll want to do that as soon as you get home. And I have at Ocean Optics conferences occasionally given a full day class just to work through this stuff. And pretty much nobody survives that without brain damage, but they do get the software at the end. Okay, so here's a real or generated sea surface that this is a patch of water 100 meters by 100 meters, and then plus or minus 4 meters here just to make it look a little better. So this was generated using all the fancy math and everything. And this sea surface exactly reproduces the Cox-Monk surface statistics. So here's the mean square slope in the X direction or along wind, the mean square slope in the Y direction or crosswind. The value for this particular surface right here was 0.031, and the wind speed was whatever, 10 meters per second. And the Cox-Monk formula is 0.036 times the wind speed, and it gives 0.032 versus 031, 021, blah, blah, blah. That's just Monte Carlo noise. DFT stands for discrete Fourier transform. So you can generate these kind of sea surfaces. It just costs you more in computer time, but you use something called the fast Fourier transform, and it actually goes pretty fast. But pretty fast means, a day of computer time as opposed to a microsecond for the Cox-Monk thing. But in the normal version of Hydrolite, you can pick, do you want to use Cox-Monk surfaces or do you want to use these Fourier transform surfaces? And it doesn't change the Hydrolite runtime because these things have all been pre-computed and stuck in there as data files. Anyway, when you do that, you generate a surface here, and then this is a 512 by 512 grid of points. Each one has its little slope and everything. And then you go in and do a lot of Monte Carlo ray tracing. And that entails more coordinate systems than you can ever want to see. And, like here's a little wave facet and light comes in and reflects and some's transmitted and it goes over and it's another little wave facet. It's reflected and it's transmitted. And I just show you this purely to discourage you from trying to do these kind of calculations because it's months of labor. Okay, does it make any difference whether you use a Cox-Monk surface or a really physically correct surface? Generally, it doesn't. Here's the irradiance reflectance of the surface for different wind speeds from 0 to 5 and 15 meters per second, and for different sun angles, and out to about 60 degrees, pretty much no difference. Once you get out to 70 or 80 degrees when the sun is right down near the horizon, then you begin seeing a difference. But even then, it's not that much. So it's, the kind of 10% sort of differences. Here's a plot here of the red is what's predicted by a Cox-Monk surface. The blue is the Fourier transform surface. This is for the sun at 50 degrees, wind speed of 5 meters per second. And you see they're almost identical out to about 60 degrees. And then you start seeing differences. And with the Cox-Monk equations, they only had the sun here high up in the sky somewhere. They couldn't really get decent measurements when the sun was, 5 degrees above the horizon. So if you use the Cox-Monk model, it's understood that it actually goes bad for the sun near the horizon or the viewing direction at near grazing angles, because you're beyond the limits of what they had data to model. And here's water leaving radiance. The red is Cox-Monk. This is for a particular sun angle, wind speed in the plane of the sun. And, they're amazingly good. So if you're looking at the sea surface from here out to 40 or 50 degrees, which is what all the satellite remote sensing is all about, Cox-Monk is perfectly fine. That is what gets used when NASA does their atmospheric correction stuff, and they fold in the sky glint business in with the Rayleigh scattering correction, and they just use Cox-Monk, and it works perfectly fine. If you really want to say, I'm on the deck of a ship and I'm looking off in that direction there, what's the reflectance from the sun? Then you really start getting at least some noticeable differences. But even then, they're not huge. Okay, enough said there. You can do all of this stuff with time dependence. Let's see, yeah, there we go. And so when the big kids in Hollywood generate a movie, and the first one that did this was Waterworld, where they have completely computer generated sea surfaces, and all the time dependence and everything is in there. So in this case, the wind is blowing in this direction, it's blowing in the plus X direction. So the waves are going across this area. This is a patch of sea surface, 100 meters by 100 meters, and 10 meters per second wind, blah, blah, blah. This is kind of a real-time simulation. There's starts over at 20 seconds. So it kind of takes, for this wave to propagate 100 meters is roughly 20 seconds. So you can generate extremely realistic sea surfaces that have both the elevation and the slope statistics, and everything's there. And when it's all over, for most purposes, Cox-Monk would have been good enough. And that only took me like 3 months of misery to be able to generate that figure. Okay, so if you really want to learn about surfaces though, what I recommend you do is get some friends together, charter a sailboat and head for Antarctica. And I've been working on Ken Voss to do this for years, and he says some way, I don't know, he lives in Miami, he likes hot weather, but I like cold weather. So anyway, what we did on my Antarctica trip, we flew to Ushuaia, which is the world's southernmost town. And then from there, we sailed down to Antarctica, kayaked along 130 miles, I think it was, of the coastline, and then sailed home. Here's the boat we chartered, and I photoshopped it in at the best scale I could to this cruise ship that showed up in Ushuaia. And our boat is basically the same size as their life rafts. So anyway, a little difference here, the Icebird, which was our boat, 60 feet, that was 951 feet long. We had a crew of 2, they had a crew of 1,200. Their passengers did not have to stand watch. Ours did. They have 3,100 passengers. We had 70. But all I can say is, like, seriously, would you rather be on this garbage scow here, or would you rather be having a real adventure on a real sailboat? And so here is the only day that the weather was good enough to. Whoops. It won't last long. Yeah, good job. Anyway, I didn't even realize I had the sound on. That's what I went through for 14 days. And you'll notice he's got a line on flipped into the what are called jack lines there. One day when I was on watch here, there's some little skylights in the top of the cabin, and I had a wave break entirely over the whole ship. And I remember looking up through the skylight, and the water was deep enough that it was green. You know, it was like 3 feet of water completely over the top of the sailboat. And so I knew it was going to be bad when we got on the boat and we headed out. And you know, they have these little like plastic containers with a big screw top lid that you buy rice and stuff in the grocery store. They issued one of those to each of us. It was like, this is not a good sign. And for the whole rest of the trip, you just walk around with your little puke pot under your arm. And every once in a while you unscrew the lid, you throw up, put the lid back on, carry on with the conversation. And I lost 18 pounds on the trip because I never got my sea legs. It was so violent that I thought, well, I'll put on a scopolamine patch. It'll wear off after a couple of days. I'll be good to go. And I never, ever got where I wasn't violently seasick. And even the first mate and the captain who had spent their last 30 years on boats, they were even seasick. And anyway, I highly recommend you do it. It's an experience. And fortunately, I had no problem gaining the weight back once I got home. So that's what it's like down there. And I think, whoops, let's go to the next slide here. There we go. So that's it for today. So it's 11, oh, it's just 10:38. Okay. So it's on for this afternoon, just nothing till 2:30, right? And we do.
Nothing till 3, no, 4 when we have the discussion.
But yeah, but Colin's going to do her geology thing at 2:30.
Tomorrow.
Oh, that's tomorrow. Okay, good. Well, I'll go do laundry and I'll be home by 4 then.
So we can, yeah, work on the project, we're here to help. And guys, again, if there's something you feel you want to see this week, if you're afraid that, you know, something even you didn't fully understand from before, something you want to get deeper into. That's it. It's the last stretch.